Ladies and gentlemen, a very warm welcome to this webinar from InApp. My name is Anil Saraswathy. I am CTO of InApp Information Technologies. We are based out of Trivandrum in India with offices in USA and Japan. First of all, I want to clear an ambiguity with the title of this webinar. If some of you were expecting me to talk about cloud migration of your IT infrastructure, my apologies. Today's webinar will be focused on cloud migration of your applications, and that too primarily from a developer standpoint. If you have any questions during the presentation, please do type them in the chat window, and I'll try to answer them towards the end of the presentation. With that said, welcome everyone once again, and let's get started. Okay, traditionally we are used to building monolithic apps that run inside one large container, just like what's shown in the slide. The application could be partitioned into several services, however, all running inside a single container. Often such applications are built by large teams where the division of responsibilities might be a bit fuzzy. To handle more users, you simply make another instance of the container and put a load balancer in front. And notice also that we have a relational database that is shared by these containers. And this is the traditional application architecture. Now, what is wrong with this architecture though? We know that deployment and maintenance would be difficult with large applications. Database designs are typically done based on a collective set of entities that make up the application, with inter-table joins and as per requirements, and making it very difficult to scale. And you know that joins are very time consuming as well. The frequency of deployment is another concern here, especially considering the rates at which customers expect new features to be added. And you know that large teams also affects the process in arriving at decisions, in taking ownership of the code, in trying out new technologies. You know, what happens with large applications is you decide on the framework and the language and the database upfront, and that's it. I mean, you basically put yourself in a mold, and then you proceed with that. And making changes becomes very difficult. And sometimes you end up having dependencies between unrelated features of your application. For example, a user management service and an inventory management service are totally unrelated, but they end up being inside the same large container. I'm talking about an ERP type of application. So that's what is basically wrong with very large monolithic applications. So what is the solution? When you think about migrating your application to the cloud, you have got to consider several aspects. Scalability, number one. You got to worry about the response times of the user, throughput, how many requests per second, how many responses per second that your application can give. Especially since it's on the cloud, you have a wide coverage, and if it's a public application, publicly consumable application, then you can imagine the number of users that can simultaneously connect and make requests to your application. Fault tolerance. I mean, how fault tolerant is your application? High availability. Is the application available all the time? I mean, what happens if there's a glitch in one of the services? I mean, does the whole thing come down because it's a single large application? When it comes down, that's it. I mean, you have a outage. Load balancing. Do you have sufficient instances of your application to balance the load? And of course, maintenance. So these are all the difficulties that you face when you migrate your application to the cloud. Now, currently there is one architecture that seems to fit these requirements. I mean, the very same keywords that I mentioned, like scalability, fault tolerance, maintenance, and so on and so forth. It's called microservices. There are several definitions for microservices out there in the internet, and I feel this is by far the best among them. Let me read this definition with you. The microservice architectural style is an approach to developing a single application as a suite of small services, each running in its own process and communicating with lightweight mechanisms, often an HTTP REST API. These services are built around business capabilities and independently deployable by fully automated deployment machinery. There is a bare minimum of centralized management of these services, which may be written in different programming languages and use different data storage technologies. This, by the way, is a definition put forth by Martin Fowler. He's an authority in microservices and CQRS, which we'll touch upon later. So as a developer, your aim should be to design microservices that are autonomous in nature. That is, have a very low coupling with other services, have very well-defined interfaces, and implement a single business capability, like, for example, inventory, shipping, accounting. These are ideal candidates for individual services within an ERP application. Yes, we are used to scaling monolithic applications by replicating the application over and over again. You can see that on the right side is the traditional approach of scaling monolithic apps by replicating the instances. However, there are some very inherent limitations. It may so happen that among the variety of features being offered by the application, only one or two requires high scalability, for example. The other features might be less used. But do we have a choice? With monolithic app, you don't, because you got to replicate the entire application as a whole. Also, by sharing the database, we are simply moving the bottleneck from the web server to the database. So in this slide, you will notice how instances of each microservice could run anywhere in the cluster of virtual machines. That's on your left side of the slide. You can run more instances of one microservice versus another. So the different color-coded hexagons that you see on the left side, they are actually individual microservices, and you can have multiple instances of them. So this slide actually shows some real-life microservices at work, like Hello, Groupon, Twitter, Netflix, and there are several more, that's coming up on a daily basis. So scalability is the #1 concern of product owners. Like I said, response times, throughput, requests per second, these are all metrics that everybody worries about. And there are 3 axes to scalability in an application. Along the x-axis, you can represent the x-axis as showing the multiple instances of the virtual machine. So you can scale your application by running multiple instances of the application. Now, on the y-axis, you can see there's a functional decomposition, which is breaking apart an application into independent services. So microservices fits in that y-axis. And then along the z-axis, you have data sharding, which is available in many RDBMS, NoSQL, and message queues, where you partition your data into different chunks and distribute them across multiple instances. So these are different ways in which you can scale your application. So microservices is definitely one way. Data sovereignty. Another term for data sovereignty is polyglot persistence. So these are words that you might come across when you Google microservices, and data sovereignty and polyglot persistence. These mean the same thing. Each microservice development team can now choose the type of database, the schema, and the location based on their preference, as opposed to having one database with multiple tables and inter-table joins for the whole entire application. For example, it is sometimes very efficient to store data about a set of soccer players, for example, sorted according to the goals they have scored in a Redis in-memory instance for quick lookups. As you know, Redis has a key value store, and the value can be a sorted set, which is sorted according to a score. So it's very efficient for you to insert a new players into the list, into the sorted set. It'll automatically sort it right at the point of insertion, so that readers can get a very quick view or list of the players sorted in the number of goals. So the response time is of key here. The response time coming out of a Redis instance versus the response time coming out of a select with an inner join from a relational database is two different things. Okay, bounded context pattern. So now I'll be addressing various patterns of cloud-based microservices. Now, each service has a private bounded data context that is accessible to only that service. Bounded context means that the service owns this data, and the service is responsible for its integrity and mutability. And this supports the very important features of independence and decoupling. Relations are often represented via universally unique IDs with no foreign key relationships possible across services. You can see here the message broker transports events across the services so that the system becomes eventually consistent, as opposed to the ACID transactions in the traditional case. So that's a big difference between event-sourced microservices versus the traditional way of doing transactions. In this example, actually, we can see we have a command to a customer service to reserve credit, which generates a credit reserved event, which is consumed by the order service and changes the state of the order record to confirmed or something. So many applications are a typical. It's very similar to this. Like you search for something, you add something, you remove something, or maybe do a calculation or two. Such type of applications can exist in an eventually consistent environment, because the end user is not going to recognize, like, I'm a few. It's a few milliseconds late that the system became consistent, so I'm getting the data. Maybe I'm getting the data a few milliseconds old or not. So people are not really bothered about that. So that's why eventually consistent systems are practically acceptable. So the single responsibility pattern, this is again key to microservices. Every microservice must shoulder a single responsibility. It makes it simple and manageable. An order service should not bother about updating the customer table with the credit limit. Instead, it should fire an order created event and then let the customer consume that event and let it do the job of updating the remaining credit and then firing the credit reserved event back to be consumed by the order service. Yes, I understand that people will be thinking, like, there are a lot of events being fired by these services, but event stores are a different animal altogether compared to databases. I mean, they can process things like millions of events per second. Actually, Apache Kafka, they have tried out a benchmark where, with just two very ordinary machines, where they were able to achieve something like a couple of million events in a second. So that's really significant. Because the basic architecture of event stores is that they are like an append only, and it's basically the nature of those stores. It's immutable. It's append only. So a lot of those features actually help them achieve that very high throughput. So this is another pattern that you come across in the microservice world. It's basically a reverse proxy for routing requests to various microservices. Especially an API gateway can act as a single entry point to your internal service architecture, which is quite a popular choice for developers as it increases security and improves user experience. So basically the request comes in, and then you would have some kind of a route map where it directs the request to the appropriate service. So if you're using Spring, if you're building your microservice application using Spring, then the Netflix contributed Zool router would be present in the API gateway container. And it is at the gateway that we usually implement common functionalities like authentication. So anything that's common to the infrastructure, you can actually implement it in the gateway. So in this diagram, you can see the user from the user interface, the request comes into the load balancer. It balances to multiple API gateways, and then from within the gateway, it gets routed to the appropriate endpoints of the microservices. So the service discovery pattern. When you scale out, you will often need to run multiple instances of a service, and their locations could change dynamically. Consequently, you must implement some mechanism that enables the clients of the service to make requests to a dynamically changing set of service instances. A registry is what we need, and that's basically supported by this pattern. A registry which maintains the currently active service instances so that clients can look up and navigate to them. Now, these patterns are all part of the infrastructure that is required to run your microservice. But it's not. I mean, if you are hosting, you could actually host your microservice in the cloud providers like Amazon or Azure or Google Cloud Platform, or you can take a VM, and then you yourself can actually run all these infrastructure components and then all your microservices among multiple VMs. That's also possible. So that's your deployment strategy, and we'll come to that soon. The circuit breaker pattern can actually prevent an application repeatedly trying to execute an operation which is likely to fail. It allows it to continue without waiting for the fault to be rectified, or might be wasting CPU cycles while it determines that the fault is long-lasting. So the circuit breaker pattern, what it does is it enables an application to detect whether a fault has been resolved as well. So if the problem appears to have been rectified, the application can attempt to invoke the operation again. So it's pretty similar to the circuit breakers that we are familiar with reference to the electrical network. So it tries to find if there's a fault. It'll just automatically disconnect that faulty piece from your system. So something very similar is the circuit breaker pattern. And Netflix has actually contributed a component called Hystrix, which is again open source, and which has been which is the de facto circuit breaker system for many microservice deployments. The load balancer pattern, I think we saw that in the API gateway slide. It's typically routing requests among multiple instances of the same service based on load. So in this slide, I've shown the ribbon load balancer component from Netflix. Typically, that library exists in any client of a microservice. In this particular case, we have the API gateway container invoking the backend microservices, and if there are multiple instances of them, ribbon actually will load balance among those instances. And this is true even if within your microservice, let's say you are invoking another microservice and that has got multiple instances. Then again, you would basically use the ribbon to load balance among them. So now we come to the event sourcing pattern. And this is pretty important because event sourcing is one of the techniques that many microservice implementations architectures are using. Basically, you divide your application into writes and reads. For example, you would be making some kind of, let's say you're creating a user or you're creating an order. Typically, that from the user interface standpoint, you will be doing a post to your endpoint with some data, and then that data is supposed to either create or update or actually post, put, delete. These are all changes that you make to your system. They modify state. And then the other side of it is the gets, which are actually queries, which actually does just nothing but reading. So that doesn't modify the state. So whenever you have situations where the state is modified, we really create an event. We don't really modify the state of the object, but instead you just create an event. So that is the basic principle with with event sourcing. And during the course of your running your application, you would find that there will be several such events being created into the event store. And with event sourcing, you can actually reconstitute the entire state of your model by reapplying these events in order. And sometimes you might have events, you can go back in history and go back and a year back and start running all the events. Still, you can be rest assured that your state, once you run all the events, your state would be exactly as it was at that instant. So you might be wondering, if you have in years worth of events, then the system would be, performing extremely slow and so on and so forth. True. I mean, if you go back, even though the event store can perform extremely well with millions of events per second and so on, still it's a little bit far-fetched if you want to run events worth a year. So what happens is you have what are called snapshots. These snapshots actually can be like you can do snapshotting, maybe a day before, or 5 minutes before, 10 minutes before, and so on. So these snapshots actually will let you run the events or play back the events from the snapshot onwards, not go back in time. But then the real advantage of event sourcing is that you get the history, you get the audit trail. You can go back. We were doing one project the other day, and that project, one of the main requirements of the project was they want a history. I mean, they want to run the system in such a way that they want to see how the world looked like on such and such a day. Now, with event sourcing, that's a byproduct of the architecture. I mean, it's a given that you can go back to on any day and look at all the events that were created for a particular object based on the model or based on the unique ID or whatever, and then you can play back and build the system, build the object, or build the models the way it looked on that particular instant. So normally, people don't refer to models as models in event sourcing. They refer to them as aggregates. And aggregate is a term borrowed from the domain-driven design to represent your model. So in this slide, you can see the order service could publish an order-created event into the system. The customer service could subscribe to the event and check for credit limit, and probably publish a credit limit not exceeded event, which could be consumed by the order service, and then it can update the state. So that's the basic principle of event sourcing. And here is a slide which shows the event sourcing with Kafka. It shows how a post request to register a user results in a create user command that publishes the user created event, which is processed by an event handler to create a record in the Postgres DB. So here the key thing is that you have to separate your application into command and events. So you have commands and then you have queries. So that's the basic concept behind CQRS, which we'll just touch upon. This is some more information about Kafka. Kafka actually categorizes its data into topics, which is partitioned across multiple instances for multiple consumers. So consumers sharing the same group name are mutually exclusive. So which means you can, for scalability, you can have actually multiple consumers running in multiple machines, for example, but then they are actually distributed, these events, equally based on load by Kafka. So that's something about Kafka. And now comes CQRS. Now I mentioned before that you can actually design your service as a set of commands and set of queries and a set of events. So commands are the writes. So on your left hand side you have the command processor, which is the write logic. You can do validations and things like that, and then you publish an event. And when you publish an event, you can have the event published to multiple consumers. So your consumer could be your own service, or it could be a different service. So in this particular case, sometimes what happens is when you might be able to this particular service might be offering multiple materialized views or reads for customers. For example, you could probably you could have a user service where your command could be to register a user, and then your materialized view would enable a reader issue a query to get a list of profiles or list of users. That could be the functionality that your user service offers. Another service might capture the same event and do something else. Maybe update something because you have a new user, so you can probably update some other data structure in some other service. So the event is the lifeblood of microservices, and CQRS is actually separating the responsibility of the command and the query. So this is an example that I just wanted to share with you, which is, in Twitter, that when you log in, you see a home timeline. And what the home timeline consists of is the tweets of the people whom you follow, your own tweets, your own reply to the tweets. That's what comprises the home timeline. And whenever one of your followers does a tweet, what really happens is an event gets posted into the system, and then that gets consumed by a fan-out service. And what that fan-out service does, it goes and looks up all the people who are the followers of that user, and then it goes and updates an area in I think it's Redis, an area in Redis where it says, okay, this user has tweeted this particular tweet and an ID of the tweet. Of course, the tweet gets stored elsewhere, but then you have the relationship between the tweet ID and the user ID who's doing the tweet, and that is getting stored in all the followers, the areas in Redis of all the followers of that tweeter. So what happens, the end result is that when you log in, when you as a follower, you log in, you have the home timeline built for you already. So that's the beauty of this event source. So instead of doing a pull-based architecture, where you go in and identify all your followers and pull data from different data sources and then present you the view, instead of that, you are actually doing a push-based paradigm, where the event is pushed into the system and then it fans out to multiple services, multiple customers. So this is another example that I just thought this would explain more in detail the event sourcing, where this is actually for a chicken farm, which we are building a microservice-based architecture application, and where you have this is actually a typical inventory type of thing, where you add 200 chickens to this particular flock, 10 of them are dead, you move 50 of them from FL3 to FL24, you ship 50 from FL3. These are all events, and these events are persisted into the event store, and then you can build your model or your aggregate by replaying these events in sequence. And of course, you can build additional materialized views for readers or gets to come in and get a response. So the ultimate result is that your response times comes down drastically. So this slide actually shows the command processing capability of an aggregate class named customer. And the framework that I'm using here is Eventuate. Eventuate is a very popular events sourcing framework. You don't really need a framework. You can build one of your own using Spring Boot and other related libraries. You can build one yourself, but this actually makes it simpler, where you define your aggregate, and then you can actually have the command processing and the event processing inside the same class. Here, it highlights the command processing capability of the aggregate class. You can see that inside the process method, you can see how the events are being created are being published into the event store. And the same class, you can see here how the event handling capabilities of the aggregate class. Basically, you're listening to your own events, and then you're processing it, how the state gets changed by playing back these events. So, this is a very simple to use event sourcing framework called Eventuate. There are several of them, but this is one that I'm a fan of. So what is the deployment pipeline like? You write the code, you build and test your microservice. You can actually do that locally on your own machine, because you're basically you have a small team, you have a small problem, and you're basically have a small set of code. Maybe 1,000 to 2,000 lines of code, not more than that. And then you build and test, and then you publish it you convert it into a Docker image. And then you deploy the Docker image to the registry. That is the typical pipeline for a microservice. And no talk on microservices is complete without mentioning reactive programming. And especially important in the context of event processing, reactive programming helps with making the most efficient use of event streams. Developers are encouraged to use reactive programming paradigms while writing event-sourced applications. And I'm a big fan of reactive programming. And RX library in particular, it has been ported to all languages. Like you have RxJS, RX.NET, RxJava, RX Python. I mean, there's difficult to find a language where the RX library has not been ported. And it's amazing, and it's a different talk altogether. I mean, it requires a complete presentation on its own. So basically, reactive programming gives you responsiveness, resilience, elasticity, and that's also message driven. So it all the more requires mention here. This slide actually shows a workflow where the microservice code is available as a GitHub repository or your private repository, whichever. And the Jenkins continuous integration pipeline actually clones it locally and runs the Maven packager to build the jar. Then it builds the Docker image for each service, and using the Docker Compose tool. So if you are familiar with Docker, then you will realize that Docker Compose is a must-have tool where you can actually mention the components that make up your application, all the microservices and other images that you need. And Docker Compose actually wraps each service inside a Docker container, runs the integration tests, and then does the Jenkins pipeline actually does the teardown of the containers and the images. So this is a typical deployment pipeline during development. Just want to mention a little bit on JHipster. I think we are almost reached our time, but I just have a couple more slides, and after that I'll take some questions. JHipster is an option if you want to quickly set up a virtual machine running a microservice application along with the infrastructure elements like the registry container, the config container, the API gateway, and so on and so forth. So JHipster, it has a command line utility. It'll prompt you with several questions, and ultimately it kind of spits out the base framework for you. So you want to try out JHipster if you're a Java enthusiast. Now, most of the patterns described earlier can be found as part of the infrastructure provided by AWS, so that you are left with writing just the command or the query part of the microservice. Basically, Amazon AWS actually provides the other infrastructure-related things. It uses the DynamoDB as the event store. I'm not very familiar with DynamoDB, so I cannot speak to how efficient it is in comparison to either Apache Kafka or RabbitMQ or any such event store. But that's basically what AWS wants you to minimize the amount of work that you do to write your microservice. So the biggest advantage, as I said, is that you don't have to manage the infrastructure. Google Cloud also have come up with something known as Google Cloud Functions, which is again very similar to the Lambda feature. The Lambda is a feature that you can see here that represents your microservice. This is a typical example of an e-commerce application where you have add to cart, cart status. These are all shown as separate services. So Google Cloud also have a similar functionality wherein it provides all the other infrastructure like the message store and everything else, and you just have to write the function. So that's why they make it very simple, and they call it Google Cloud Function. So coming to the various microservice frameworks out there, if you're programming in Java, then you can use Spring Boot and Netflix. JHipster, as I said, is it uses Netflix OSS and Spring Boot, and it actually automates the process of building a skeleton application. If you're a Node.js programmer, then Seneca and AquaJS is worth exploring. Python, ZeroMQ, .NET has got Service Stack. And of course, AWS has Lambda, Azure has Azure Service Fabric, and Google has Google Cloud Functions. So that actually completes my presentation. I hope you all learned a little bit of additional information on how to migrate your application to the cloud. So let me just see, the questions that we have received here. Won't microservice architecture create a lot of event traffic, and how does it affect performance? Yes, basically that's what I had hinted at before in my talk. Yes, it does create a lot of events, but that's what the event store is designed for. It's designed for very high volumes and performance, and people have actually are running event store, have been running event store applications for several years, even before the concept of microservices came up, and they have been running really successfully such event stores. They're usually append-only and immutable databases, so that probably is a big difference compared to RDBMS. And as I said, Kafka has been benchmarked with a couple of million writes with just a couple of ordinary machines. Then, of course, using event sourcing automatically brings in audit capabilities to the system, which is a byproduct. Okay, let's see the next question. Okay, this question, it says, can we use a single common database for your microservices? Yes, yes, definitely that is a possibility. You can use a single common database, provided you do not have any foreign key relationships among the tables owned by the different microservices. I'm assuming that each of your service is going to have its own private data context, which means private set of tables which has no connectivity through foreign keys. There cannot be any joins across the bounded context of these services. Any other question we have? Okay, can microservices be written in any language? Yes, that's the beauty of microservice, because it executes as a process within a VM. It just listens to an IP address and a port, so you can write it in any language and any database of your choice. No problem. So I think that's pretty much it. Thank you, everyone, for taking the time to join this webinar. All registered folks should get a recording of the webinar via email in a couple of days. And thank you again for joining, and have a wonderful day. Bye.